Alright, welcome to my lecture. So we're talking about infinite series, and I want to discuss specifically the integral test. Okay, so let's just state the integral test. Okay, this is one of the most important tests for determining if a series converges or diverges. Okay, and it says this. It says let f of x be a continuous positive decreasing function on 1 to infinity. And here, this sequence that we're considering is just the function itself made into a sequence. So that is, the sequence a sub n is just f evaluated at that integer n. Okay. Then this series from 1 to infinity of a sub n is convergent if and only if the improper integral So how I like to state this is that the series converges or diverges with the improper integral. And one side note is that we don't have to start at 1 in either the improper integral or the series. We only need to determine if it is convergent from some point on to infinity. Any point. It doesn't need to be 1. Okay. And I'm just going to work out an example with this. And it's more or less the proof. Okay. So one thing that I would just say is this. Okay. The series, and let me call this S sub n, which is the partial series. So maybe I'll put this word. The partial series S sub n, which is the sum from 1 to infinity of a sub n, is a sequence. After all, a sequence is just a list of numbers. And if I was to write out S sub 1, the first term in the sequence would just be a sub 1. S sub 2, and by the way, I apologize, there's one thing that should have been written differently in this series, I'll put it in red here, is the summation. The upper summation should correspond to B capital N. Okay. S sub 2 is the sum from n equals 1 to 2 of a sub n, and that is a sub 1 plus a sub 2. S sub 3 is the sum from n equals 1 to 3 of a sub n, and here is just a1 plus a2 plus a3, and that's a number. All of these numbers are getting bigger. So in particular, if I was to look at S sub n, this is going to be the summation from n equals 1 to capital N of a sub n, and it's going to be a1 plus a2 plus a3 all the way to the a sub n. This is a sequence of numbers. After all, a sequence of numbers is just any list of numbers. Okay. So the sequence that I'm referring to corresponds to what's called the partial sums of a series. Okay. So notice, since each term of a sub n, so here a sub I is greater than 0, so s of n is increasing, is getting bigger, because I'm adding more positive terms to it with each sequence. The question is it bounded? So by the monotonic sequence theorem, S sub n converges, and what it means to converge is that this limit as n goes to infinity of S sub n, which is this limit as n goes to infinity of this partial sum from n equals 1 to little n of a sub n, and I can just put that infinity in that superscript as another way of writing this, is if this infinite series converges. Okay, this converges if S sub n is bounded. Okay. And it turns out that S sub n is bounded by the improper integral. Okay, so here's going to be the fact: S sub n is bounded by an improper integral. Okay, let's work out this example. So the question is, does this summation from n equals 1 to infinity of 1 over the square root of n converge or diverge? So notice it's not asking you what value it is. It's asking you, does it converge or diverge? Okay. And let's just work this out. So I'm going to write out what this is. I'm going to write out this summation. I'm going to write out the first few terms. Okay. And first, we're going to note, hey, f of x, the corresponding function here, is just going to be formed by replacing n by x. Okay. And if I was to graph this, right, this function is always greater than 0. Okay. This is a rough sketch of the graph of f of x, and I'll just label the x-axis there, and there's the y-axis. And if I call this 1, and this 2, this 3, hey, look, I can form the area under this curve, and maybe I should do this in blue. Okay. Well, let's look at this area of this one little rectangle. Is going to be height 1 and width 1. That's going to be the area. So each width that I have here is width 1. Okay. If I look at this one right here, you know, I can see that, hey, I'm going to have a height of 1 over root 2 multiplied by a width of 1. If I look at 3, this is going to be 1 over root 3 multiplied by 1. And I can keep going in this way, so I'll just put dot, dot, dot. Well, what you should notice is that there's more area formed by these blue rectangles than under the curve. So in this case, I should note this, that this integral from 1 to infinity of f of x dx, this is less than or equal to this summation from n equals 1 to infinity of 1 over root n. And 1 over root n, this is going to be 1 plus 1 over root 2 plus 1 over root 3. Hey, that's the areas of each rectangle, each of the blue rectangles. And if I kept going, if I inscribed more, this would have been 1 over root 4, etc. That this area is greater than this integral of f of x. Well, let's calculate this integral. This integral is going to be this limit as b goes to infinity from 1 to b of 1 over the square root of x dx. And I can integrate this. So let me do that. This will be this limit as b goes to infinity of this integral. This integral is going to be the antiderivative of this, which will be positive square root of x, is going to be multiplied by 2 and evaluated at 1 and b. So let's evaluate this limit. Limit as b goes to infinity of 2 root b minus 2 root 1. And this limits to be infinite. So what this says is that infinity is bigger than or equal to the summation from n equals 1 to infinity of 1 over root n. So this must also be infinity. I mean, the only thing bigger than or equal to infinity is infinity. So this is infinite, and we would say in this case that it's divergent. Okay. Let me give you another example. And this would be just asking you, does this summation from n equals, let's do 2 to infinity of 1 over n cubed, does this converge or diverge? Okay. So one thing that I'm going to do is I'm going to note, hey, the corresponding function for this is f of x is going to be 1 over x cubed. Let's graph this. I'm only going to graph the positive part. The graph of this looks very similar, but you should notice it hugs the x-axis a lot closer. Okay. Now what I'm going to do is I'm going to start inscribing things. Okay, and I'll inscribe it in blue again. So here's going to be 1, here's going to be 2. I'm going to inscribe it starting at 2, but I'm going to draw back so that this rectangle has a height of 1 over 2 cubed. So this is 1 over 2 cubed. That's the height. The width is 1, so the area is 1 over 2 cubed. I'm going to go to 3 here, and here's going to be this one. This is going to have area 1 over 3 cubed. Then let's go to the next one, 4. That's going to be 1 over 4 cubed. And then I'll just put dot, dot, dot. So I think you get the idea here. Okay. And one thing that you should notice is here, I inscribed it so that the area was an underestimate, i.e. I get this integral. So this is the relationship. The area of this integral from 1 to infinity of f of x dx. This is more than, so the inequality is flipped. It's more than the blue area. And I'll put this in blue. So this is more than this summation from n equals 2 to infinity of 1 over n cubed, which is the area of 1 over 2 squared, if I just plug that in, plus 1 over 3 cubed, plus 1 over 4 cubed, etc. And it keeps going. So now I'm going to go ahead and calculate this little piece, this integral, and I'm going to put this limit as b goes to infinity, because I need to deal with the improperness, the integral from 1 to infinity of 1 over x cubed dx. And this is just this limit as b goes to infinity of x to the minus 2 divided by a negative 2. So I'll put the negative out in front there. I'll evaluate at 1 and infinity. Not infinity, I apologize. I did not deal with the improperness correctly, so I apologize. Because I put that limit here, I need to put the b. Okay, so this will be limit as b goes to infinity, just plugging in the limits of integration. This will be minus 1 over 2 b squared plus 1 over 2, just plugging in x equals 1. And we see that as b gets larger and larger, that quantity gets closer and closer to 0. And so we get 1/2. So in summary, this sequence from n equals 2 to infinity of 1 over n cubed, this is bounded. It's less than or equal to 1/2. So this is bounded by 1/2. Okay. Notice the sequence S sub k, which will be the summation from n equals 2 to k of 1 over n cubed. And this is also known as a partial series because a series is a sequence. So this is a partial series, is increasing. Okay. So it's bounded increasing. So since it's bounded increasing, and by the way, if you're curious why it's increasing, why don't I just quickly show you. Increasing, well, if I had s sub 2, this is going to be 1 over 2 cubed. If I had s sub 3, this is going to be 1 over 2 cubed plus 1 over 3 cubed, my apologies. S sub 4 is going to take the previous term and add 1 over 4 cubed. So it keeps getting bigger, and it keeps going like this. Okay, so it's pretty obvious that each term, as I increase k, gets bigger. Okay, so by the monotonic sequence theorem, so if it's convergent, right, by the monotonic sequence theorem, S sub k is convergent, and maybe I should say why. So because it is bounded, right? It's bounded by 1/2. We proved that. And increasing. So this monotonic sequence theorem is very important. And what this means is, i.e., this limit, as I'll put k goes to infinity of S sub k, is equal to this limit as k goes to infinity of this summation from n equals 2 to k of this 1 over n cubed. And we can go ahead and put that in the superscript as is commonly written. So i.e. this is convergent. That is, it's finite. Okay. All right, so that is a rigorous proof that 1 over n cubed converges. And key to all of this, I'll just reiterate it, key is this integral test. And I'll write it in a slightly different form. It says that this summation from n equals a to infinity, I guess I can't use a again, so I'll use the sequence to be b sub n, is convergent, converges or diverges, so let me phrase it differently. Converges or diverges with the improper integral of f of x dx, where we have that this b sub n is equal to f of n, and these are all terms that are non-negative. Okay, thank you very much. You will be using this integral test quite a lot. Okay, thank you.